Welcome back to the deep dive. Last time, we sort of kicked off our look at the portability chapter in the Ada style guide.
Right, we covered the fundamentals, numeric types, storage control,
Hmm.
groundwork, really.
Exactly. We saw how things like being careful with assumptions and really crucially encapsulating platform specifics are, key building
They
blocks.
absolutely are. Those strategies are foundational. But Ada, well, the language by design, it gives implementers quite a bit of flexibility in certain areas,
Oh,
often the areas closest to the actual hardware or the operating system. And, well, that's precisely where portability can get tricky.
right. Okay, let's unpack this. Today, we're diving into those trickier zones. We're going to look at exceptions, then wade into representation clauses and other, let's say, implementation-dependent features, and finally, tackle input-output.
hmm
Our mission today is really to guide you through the style guide's advice on navigating these potential minefields so you can understand where the pitfalls are and how to avoid them, or at least contain them.
Exactly. These sections in the style guide, they really highlight the specific points where compiler writers and runtime systems have some latitude. If you're not careful, code that runs, perfectly on one platform might just fail or behave unexpectedly on another.
So the guide is like a map for those dangerous corners.
You could say that, yeah. It helps spot them.
All right, let's start with exceptions. Now, exception handling, it's a standard language feature, right? But even here, apparently, surprising portability issues can pop up.
They can.
You might think, say, constraint error is always raised for the same specific reason in the same specific place, but the style guide warns us, maybe not.
That's the first key insight here. Guideline 5.1 basically tells us don't depend on the exact locations where predefined exceptions are raised.
Okay.
The Ada Reference Manual, the ARM, the language rulebook, it actually allows implementations to raise an exception like constraint error for the same underlying cause, but for different points in the code.
So if I write a handler that assumes constraint error must mean, I don't know, array index out of bounds right here at line X.
Then you're probably building in a non-portability, yes.
Okay.
And it's more than that. A single predefined exception can cover multiple conditions. Constraint error is a classic example. It's used for a whole range of things, not just indexing.
Right.
The guideline also says don't rely on behavior from the standard Addo exceptions package beyond the absolute minimum defined in the ARM.
Because vendors might add their own stuff there too.
Precisely. Implementation-specific features. So while, using local blocks for handlers can help narrow down what might have gone wrong, you fundamentally can't rely on the exact origin or any extended capabilities.
Makes sense. Your handler needs to be robust for the type of error, not the specific manifestation or some vendor extension.
Exactly.
Now, if predefined exceptions have these subtleties, what about exceptions defined by the implementation, the vendor-specific ones?
Now we get to a much stronger directive. Guideline 5.2. It's pretty firm on this.
Okay.
It says, basically, do not raise implementation-specific exceptions, period. And if you encounter one, say coming from a library call or the runtime,
Yeah.
you should convert implementation-specific exceptions within interface packages to visible user-defined exceptions.
So encapsulation again. This keeps coming back, doesn't it?
It absolutely does, and for a really critical reason here. Vendor-defined exceptions are explicitly not guaranteed to be the same across different compilers or platforms.
Right. Different names, different triggers.
Exactly. Their names will likely be different. The conditions that trigger them can vary wildly, or, they might not even exist on another platform.
So if you let those leak into your main code...
It's a porting nightmare. You'd have to hunt down and rewrite exception handlers everywhere.
Yeah, sounds awful.
It is. But if you catch that vendor-specific exception inside a low-level interface package, the one that deals with that specific functionality, and then raise one of your own well-defined user exceptions, you achieve two things. One, you hide the non-portable name and behavior. Two, you localize the dependency to just that one interface package body.
Right. So when you port, you only need to change that one specific place.
Precisely. Not the thousands of lines of application code that might handle the generic exception you defined.
Got it. So for exceptions, predefined ones are unpredictable in their exact location and details, but implementation-specific ones, actively dangerous for portability. contain them.
That's the core message there, yeah. Now let's transition to a section that deals with some of Ada's really powerful features, the ones that let you get closest to the machine.
Okay.
And consequently, these involve some of the most significant portability risks, representation clauses, and implementation-dependent features.
All right, this is where Ada lets you control memory layout, bit positions, calling conventions. The stuff compilers usually handle automatically. Sounds like a place where implementations have to differ.
They also do, yes. Ada provides these capabilities for systems programming where you might need that level of control, maybe interacting with hardware or specific data format.
Yeah.
But it almost always comes at a portability cost. The main defense, again, isolation.
Isolation, got it.
So Guideline 6.1 is about representation clauses themselves. It starts with the ideal advice. Use algorithms that do not depend on the representation of the data.
Meaning, if you can write the code without forcing a specific memory layout or size, just do that.
Absolutely.
Yeah.
Unnecessary representation clauses, they just add complexity, they make assumptions about the target architecture, and, well, they might not even be supported by a different compiler.
But sometimes you need them.
Exactly. The guideline acknowledges that, specifically when accessing or defining interface data or when a specific representation is needed to implement a design.
Like talking to hardware or following a network protocol.
Classic examples, yes. The outside world dictates the representation in those cases.
Okay, that makes perfect sense.
But here's a really interesting, maybe surprising point from the rationale. It says, do not assume that sharing source files between programs guarantees the same representation of data types in those files.
Hold on. If I have the exact same source code file, why wouldn't, say, a simple integer type have the same representation, even on the same machine, maybe compiled at different times?
This is where that compiler freedom comes in again.
Yeah.
Without a representation clause explicitly forcing a specific size or alignment or layout.
Yeah.
The compiler is free to choose what it thinks is most efficient or convenient for the target architecture and the current compilation settings. Things like the compiler version, optimization levels, the order things are compiled, even details about the underlying system.
Wow. All that can change the representation.
It can influence the choice, yes. So code that relies on implicit assumptions about representation, like treating a record as just a sequence of bytes without an explicit layout clause that can easily break.
Even if you compile the identical source code, just with different settings or maybe a newer compiler version.
Exactly. It really highlights why, during a port, you need to look closely at every representation clause. They might be necessary, but they're also potential points of failure or might need rethinking.
That's subtle, but really critical. The compiler has freedom unless you explicitly constrain it. Okay, what about using constants from the predefined package system? That's Guideline 6.2.
Right. The guideline advises, avoid using package system constants except in attempting to generalize other machine-dependent constructs.
Why avoid things like system.storageUnit or system.addressSize? They seem useful for, understanding the machine you're on.
They are useful, but their exact values are implementation provided. If you use them directly in your logic, you might be binding your code tightly to assumptions about those values.
And those values can change on another platform.
Leading to unexpected behavior, yeah. For example, system storage unit number of bits in the smallest addressable units, often 8, but not always. Code, assuming it's 8, might fail elsewhere.
So the exception is using them to parameterize other implementation-dependent things.
Right, that's a form of isolation. You use system.storageUnit, perhaps, to calculate a size in a representation clause rather than hard-coding 8-pick. It centralizes the dependency.
Okay, so system constants.handle with care, taking it even lower level. Machine code inserts. Guideline 6.3.
The advice here is very direct. Avoid them, full stop.
That sounds pretty definitive. Why such a hard line?
Well, first off, the package that even allows machine code inserts, it's optional according to the ARM. It's an Annex C, system programming.
So a compiler doesn't even have to provide it.
Correct. And even if it does, the syntax for the inserts, totally implementation defined. But more fundamentally, the actual assembly language, the register conventions, all those low-level details.
They're going to differ wildly between processors, operating systems.
Exactly. Code with machine code inserts is inherently tied to a specific compiler, a specific OS, a specific chip. It's basically the definition of non-portable.
So using machine code is like saying, this code only ever runs here.
Pretty much. The guideline does allow an exception, but only if you are absolutely forced by requirements, and you've proven that higher-level Ada constructs just can't do the job.
And if you do have to use them.
Document everything extensively. Why it was necessary, what you tried that failed. So anyone porting it later understands the absolute constraint.
Got it. Absolute last resort, document everything. Okay, what about interfacing to foreign languages? Guideline 6.4. This feels like a really common practical scenario.
It is very common, and yes, it's a significant portability challenge. The guideline strongly recommends preferring the standard interfaces package and its children like interfaces.c, interfaces.fortran.
Use those over any implementation-specific ways of calling foreign code.
Definitely. And for interfacing to static subprograms, functions, or procedures in the foreign code, the guide suggests using pragma import rather than access to subprogram types.
Why is Pragma import preferred there?
The rationale mentions it provides a better solution because for static calls, you don't need any indirection. You're directly calling the foreign routine. It's generally cleaner, especially if you use the external name argument.
Ah, external name versus link name. What's the difference again?
All right, common point of confusion. External name is the name of the thing in the foreign source code, like the C function name CBRE. Link name is the symbol the linker needs to find. You usually
Oh.
want external name for clarity, and sometimes it helps portability because linkers might, decorate names differently.
Okay, so standard interfaces, Pragma import, use external name, and where should all these interface pragmas import export convention as live in the code?
The guideline is very clear. Isolate all uses within implementation-specific interface package bodies.
More isolation. It really is the recurring theme, isn't it?
It's the core strategy here, absolutely. Interfacing involves complex details, data type mapping, parameter passing, calling conventions, linker behavior.
All sorts of things that vary between compilers and operating systems.
Exactly. By putting all those pragmas and the low-level interface details in the body of an interface package, you hide that messy, non-portable stuff from the rest of your application.
And the application just sees the clean ADA specification of your interface package.
Right. When you port, you rewrite the body of that package for the new target,
Yeah.
and hopefully the rest of your code remains unchanged.
The source had that example of calling a CBR function, the cube root. Can we quickly walk through how that structure works?
Sure. So you have a C function, say double CB or T double X. In Ada, you'd make a package spec, maybe mymathlib, defining an Ada function, let's call it cube root, taking and returning float, or whatever Ada type makes sense.
Okay.
Then in the body of mymathlib, you declare an internal function, say CCBRD. This one matches the C signature using types from interfaces.c, like interfaces.c double.
Ah, so it uses the specific C types from the standard package.
Exactly. And the CCBR function is where you put the pragma import. You'd specify convention C and external name CBRT.
And then the visible cube root function, the one the rest of your Ada code calls.
That function in the package body just calls the internal CC burret. It handles any necessary type conversions between the Ada float and the interfaces.c double.
I see. And it can handle error checking, too.
Yes, absolutely.
Yeah.
Any checks, like maybe ensuring the input isn't negative for a real cube root or catching potential exceptions from the C side, you'd handle that within the cube root implementation in the package body, maybe converting errors to a standard Ada exception like argument error.
So the whole messy, non-portable C interaction is nicely wrapped up and hidden.
That's the goal. The guideline does note an exception. Sometimes low-level hardware stuff in embedded systems has to use foreign calls. But even then,
Isolate and document.
isolate and document. It's the mantra for this whole section, really, which applies just as much to implementation-specific pragmas and attributes, I assume. Guideline 6.5.
You assume correctly. Avoid pragmas or attributes added solely by the compiler vendor.
The rationale seems obvious.
It is pretty simple. They're specifically designed for that one implementation. They're highly unlikely to work or even exist on another compiler. Always prefer standard features defined in the annexes if something similar exists there.
Using vendor-specific features is basically opting into vendor lock-in.
Pretty much, yeah. Now, let's briefly touch on the unchecked operations. We've got unchecked deallocation, 6.6, unchecked access, 6.7, and unchecked conversion, 6.8. These all bypass some of Ada's safety features, right? Which sound like a portability red flag immediately.
It is. Okay, starting with unchecked deallocation. It lets you manually reclaim memory. It's a standard feature, syntactically. But the guide says avoid dependence on it. Why is a standard feature potentially non-portable?
Good question. While Ada unchecked deallocation is standard syntax, its behavior and how it interacts with the runtime storage management. The source calls that extreme implementation dependence. It overrides the default storage reclamation timing, which is platform-specific. Using it risks creating erroneous programs, use after free bugs.
And whether that bug actually shows up or how it shows up could depend entirely on the target's memory allocator, or maybe if there's garbage collection, or even just how much memory pressure there is at that moment.
Exactly. It gives you low-level control, but at a significant portability risk. The guide notes it can be useful sometimes, maybe for managing storage tightly in recursive algorithms for performance, but it stresses it's still risky.
So even though the feature exists, relying on the precise timing or the exact consequences of that manual deallocation is where the portability problem lies.
Precisely. What about unchecked access then? Guideline 6.7.
Avoid dependence on the attribute unchecked access. Its main job is to bypass accessibility checks.
The safety net that prevents dangling references, pointers to memory that's no longer valid.
Right, so if you use unchecked access, you become responsible for guaranteeing that pointer is always valid. But the memory landscape, the address space, allocation patterns, that's all highly implementation dependent. Making those guarantees reliably across platforms is very difficult and non-portable.
Okay.
Risks dangling references that behave differently.
Got it. And unchecked conversion. Guideline 6.8.
Again, avoid dependence on ADA.unchecked conversion. This one bypasses ADA's strong typing. It lets you treat the bits representing one type as if they were another type.
Like interpreting an integer's bits as a float or something.
Exactly. But implementations are allowed to limit which types can be converted and what the result means, especially if the object sizes are different. What works as a bit pattern reinterpretation on one architecture might be totally invalid or just mean something completely different on another.
Are there any acceptable uses for it, according to the guide?
Yes, it does note exceptions. It can be useful, but only in isolated, explicitly implementation-dependent parts of the code, like low-level programming or maybe inside that foreign language interface package we discussed. It's exactly, keep it contained. Also interestingly, the source points out it's the only standard way to reliably get the internal integer code of an enumeration value if you've used an enumeration representation clause to define that specific mapping yourself.
Ah, okay. So niche uses, but again, keep it contained and justified.
Isolation again. Okay, finally, in this big section on low-level stuff, runtime dependencies, guideline 6.9. What's this about?
This is about avoiding direct calls or implicit reliance on the underlying operating system or the ADA runtime system itself, unless the interface you're using is explicitly defined as standard in the ADA language.
Like the interface is defined in Annex C, system programming, or Annex D, real-time systems.
Exactly. Use standard bindings the language provides, like ada.command for command line arguments, and always prefer features defined in the annexes over vendor-specific runtime calls if they cover your needs.
So don't just, call the cmalloc function directly or some specific Windows API call, unless Ada gives you a standard defined way to interface with that kind of OS feature.
Precisely. Any feature not explicitly specified in the ARM will almost certainly behave differently or just not exist across implementations. Annexes C and D, for instance, they standardize some common low-level or real-time needs. They provide a portable interface if your target implementation actually supports that annex.
Right, which contrasts sharply with calling functions specific to your, say, Windows development machine, which definitely won't exist on your embedded target.
Exactly. The guideline does acknowledge, though, that in real-time embedded systems, interacting directly with low-level hardware facilities is often unavoidable.
And in those cases,
Treat it like machine code inserts. Document why it's absolutely necessary and isolate it. Ideally, hide it behind an interface package whose body can be swapped out for different targets.
okay, so the big takeaway for this entire section on representation clauses and implementation dependencies is these low-level features are powerful, yes, but they come with significant portability risk because they touch implementation details directly.
And your defense strategy is recognize them, justify their use if you absolutely must, document them thoroughly, and always isolate them, usually within a dedicated interface package.
You've got it. It's about strategically managing the non-portability where it's unavoidable, not letting it sort of infect your whole code base.
All right, let's move on to the last major area for today, input-output. Now, unlike some languages where I/O might be built into the syntax, Ada handles it mainly through standard packages, right? Like Ada text I/O or Ada sequential I/O.
That's right.
Does this package-based approach help with portability?
Well, it definitely standardizes the interface you call from your Ada code, which is a huge plus. But the implementation of those packages still has to talk to the outside world.
The file system, network sockets, embedded hardware.
Exactly. And that interaction point is inherently non-portable, so it leads to a different set of challenges. Isolation, again, is going to be the main defense strategy.
Okay, Guideline 7.1 deals with name and form parameters. What are those?
These are parameters you pass to procedures like create or open in the I/O packages. The name is typically the file name or device identifier. The form parameter provides implementation-defined control over file properties, things like buffering, record size, access modes.
And the guideline says?
Use constants or variables for these name and form parameters. And crucially, define and initialize these constants in a dedicated implementation dependency package.
Why? Don't file names look pretty much the same everywhere, like path to file or C path to file?
Not necessarily, and the rules can differ subtly, but the real variability often comes with the form parameter. Its format, the valid values, what they mean that can vary hugely between operating systems and compilers.
Ah, I see.
If you hard-code literal strings for name or especially form directly in your application code, porting becomes really difficult. By putting them in constants in a separate package body, you only need to change that one package when you move platforms.
Makes sense. And the guide also warns that just leaving form out or using a null string doesn't guarantee portability either.
Right, because even the default behavior can vary between implementations. The source even suggests you might want to abstract the create and open calls further, maybe in your own interface package, to hide the form parameter entirely from the application code.
Another layer of isolation. Okay, seems simple, but important. Next one looks straightforward. File closing. Guideline 7.2.
Yeah, this one's simple. Explicitly close all files you open.
Why is that critical for portability?
The rationale is basic. The ADA standard doesn't strictly define what happens to external files, like flushing buffers to disk, releasing file locks if they aren't explicitly closed before your main program finishes.
So the file might be left in an inconsistent state, or maybe temporary files don't get deleted properly.
Exactly. The behavior might vary. Explicitly closing is just good practice anyway, and it ensures consistent, predictable behavior across platforms.
Good hygiene, basically. Got it. Now, input-output on access types, guideline 7.3. This just sounds fundamentally like a bad idea for portability.
It generally is. The guideline says avoid performing I/O on access types. That means trying to write the value of a pointer or an access variable to a file, or read one back.
Why is that so bad?
Well, the effects are simply not specified in the language standard. But think about it. When you write the value of an access type, what are you usually writing?
A memory address, presumably?
Right. And that memory address is completely meaningless outside the specific process, the specific runtime environment, the specific memory space it came from.
So if you try to read that address back later, maybe on a different machine, or even on the same machine after memory has been reorganized?
It's highly unlikely to point to anything valid, let alone the original data you thought you were pointing to. It completely bypasses ADA's type safety and relies on a memory layout that's totally implementation dependent and transient. It just doesn't make portable sense.
Okay, that's a very clear reason. Don't write addresses to files. Next up, package data streams, stream I/O, guideline 7.4.
Right. The guideline here suggests you should consider using sequential I/O or direct DO instead of stream I/O unless you genuinely need stream I/O specific capability, which is low-level heterogeneous I/O.
Heterogeneous meaning?
Meaning files containing items of different types mixed together. Sequential I/O and direct I/O are designed for homogeneous files where every item in the file is of the same type.
And they enforce that at compile time.
Yes, which is a safety benefit. Stream I/O, on the other hand, deals with raw sequences of bytes that represent objects of potentially different types. To read a stream I/O file correctly, your application needs some kind of external knowledge. It has to know the order and types of data that were written into that byte stream.
Which sounds more complex and potentially error-prone.
It can be. So the guideline basically says, for simple, uniformly structured data files, the compile time safety and relative simplicity of sequential I/O or direct I/O make them often preferable. They're arguably easier to reason portably. Use the simpler, safer options unless you really have that requirement for mixed data types in one stream.
Okay, stick to simpler I/O unless the heterogeneous stream is truly necessary. Makes sense. Finally, current error files, guideline 7.5.
This suggests considering the use of current error and setter, which are provided by Ada Text I/O, specifically for handling runtime error messages.
How does that help portability?
Well, Text I/O has this standard concept of three logical files: current input, current output, and current error. By explicitly directing your error messages using setter or writing to the file designated by current error, which often defaults to the system's standard error string.
You get more consistent behavior than just, say, writing error messages to standard output.
Exactly. It can increase portability, especially for interactive applications, because How standard output and standard error are handled or redirected can vary more between environments. Using the designated error stream is generally more robust.
The source shows an example using Ada text.io standard error directly in an exception handler, which seems pretty clear.
It is clear and standard. The notes also raise an important related point, though, tying back to earlier guidelines we haven't covered today about tasking.
Ah, concurrency issues.
Right. Be aware of potential problems if you have multiple tasks trying to modify current input, current output, or current error at the same time.
Because the state inside the text.io package that tracks which file is current isn't necessarily protected against concurrent access.
Often it isn't, yes. It reinforces the need for careful design when tasks share access to global resources, even seemingly standard ones like I/O streams.
So even a standard I/O package can have portability or at least correctness issues if you're not careful with tasks.
Precisely. It's always about understanding the underlying model and any shared state involved.
Okay, wow. We've covered a massive amount of ground today, finishing our deep dive into the portability chapter of the Ada Style Guide. We looked at exceptions and their subtle variations.
How low-level features like representation clauses and interfacing expose really significant implementation differences.
And how I/O, even though it uses standard packages, still interacts with a non-portable external world.
And across all these areas, exceptions, representation, foreign calls, those unchecked operations, I/O, the consistent theme really, is recognizing where the language standard gives implementers freedom, or where interaction with the outside world happens.
And the strategy is always either avoid relying on those specifics, or if you can avoid it,
Then carefully isolate that dependence, usually using Ada's strong encapsulation features, like putting the tricky stuff inside package bodies.
encapsulation as your primary defense against portability headaches, it just kept coming up because, well, it works.
It's a fundamental strength of Ada, and the Style Guide really leans into it for building robust, maintainable, and portable systems.
So what does this all mean for you, the listener, working on your own Ada projects? We've outlined the risks in these specific areas and the strategies the Style Guide recommends, but it does bring up a really fundamental question for almost any real-world project, doesn't it? You often need to use powerful features. You might need to interact directly with hardware or call foreign code for performance or access some specific system service. These things are often inherently implementation dependent.
That's true.
So how do you balance that necessary use of potentially non-portable features with the desire, or maybe the requirement, to make your code portable to future platforms or different environments? Where do you draw the line in your projects between getting the most performance or control today and ensuring flexibility for tomorrow?
That really is the critical design trade-off, isn't it? It's rarely all or nothing. It's usually a strategic decision based on the project's specific needs, its expected life, the target environments, lots of factors.
Something definitely worth mulling over as you apply these guidelines. Thanks for joining us for this deep dive.